you. So just there, yay. Okay, so this is the worst talk to have, to be here if you have a hangover, because there's going to be assembly and there's going to be C++. Anyway, this talk is about sins and confessions. So what sins? Well, I've been working for a bunch of audio companies in the last few years, and I've always been focusing on real-time safe code. And this talk is about the 7 most common mortal sins I've seen working for these companies. And confessions, well, Dave and we did a talk 4 years ago called Real-Time 101, and it's my most viewed talk, yay. And I've heard at least 3 people say they use it for onboarding their new employees. And a bunch of other real-time talks reference this talk. And so my confession is, there's nothing major wrong with the talk, but I think if I would give the talk now, it would be a slightly different emphasis. So yeah, I think both mics are on for some reason. Okay. So this is an advanced intermediate talk, so if you're watching this online, there are some prerequisites. It would be good if you know what a std-atomic is, and if you would know what a mutex is. And if you don't, well, you can watch that Real-Time 101 talk, or you can watch Timur's talk that he gave this year, which is a really, really good talk, and I highly recommend that talk. Also, I have a lot to get through, so if you have questions, then just write down the slide number, and then we'll get to that at the end. Okay, so the 7 sins. What do I mean with a sin? We're talking about real-time code, so obviously a sin is if there's some violation of the real-time guarantees, but really closely related. When we write real-time code, we often use atomics, and it's really easy to write data races. So I'm going to be talking about both, not only real-time violations, also data races. So what's the most common sin I see in code? It's something like, that printf, oh, that was just meant for debugging, or oops, I by mistake allocated on the audio thread, or I forgot to write the ampersand. And so now I'm taking a copy instead of a reference on the audio thread. So what do I mean with this? I mean, the #1 bugs in real-time code by far are just typos, lapses of concentrations. If you ask the developers why they did that mistake, they all knew better, right? So those are by far the #1 bugs in real-time code. And they can be really hard to find, like a missing ampersand. So what we really need is good tooling and diagnostics. So maybe the biggest sin is not using good tooling and diagnostics, right, to catch those errors. And when we talk about diagnostics, there are kind of 2 things I distinguish between: detecting data races and detecting real-time guarantee violations. So data races are fairly easy to detect. You just use the thread sanitizer. It has the downside that low-level lock-free data structures, sometimes you get false positives in them. But there I recommend this attribute that you can just slap onto a function, and then it won't analyze that function. And then the second thing that we want to diagnose are real-time violations. And unfortunately, that's much, much, much harder. There's no automatic way to detect this. The best you can do today is attach a tracer. I use dtrace a lot, that's macOS Linux. You can also use perf. And then you tell the tracer which functions are not real-time safe. So if you were, let me see if I can get my pointer. If you were using a dtrace, you would write such a script and you would list all the functions that are not real-time safe. And then additionally, in dscript, you would basically filter, or you would add this conditional so that it only tells you about the violation if the thread was a real-time thread, right? You can do something similar on Linux. But this has some big downsides, right? You really need to think of all the functions that might not be real-time safe. And that means if in your code you write something that has some kind of loop that might spin, you need to remember to add that to that list. And even worse, if the optimizer decides to inline one of those functions, well, then dtrace can't do anything. You won't detect that violation. So I think there's still some room for better tooling, and so I'm really looking forward to a talk that's this afternoon by David Trevelyan. They've apparently implemented a real-time sanitizer, so yeah, let's see. see what that's about. Okay, so that was sin number 1. Sin number 2 is a bit of a strange one. So I talk a lot about real time, both public talks, but also at companies. And so often people come to me after the talk and say, really great talk, but all that is not necessary for my machine because the machine that I'm running on has this feature or this limitation, right? And maybe one concrete variant of this is, I worked for a company that had an embedded system. They had a single core, and they were like, we don't need all that stuff. We just have a single core. There's not multiple cores that can access memory at the same time. And who said that exact quote? It was actually me 10 years ago. Just started at the Juice team, and I remember Timur looking at me and saying, I don't think you're right, Fabian. So why did I say that? It's because, well, even if you have a single core CPU, and even if you have a cache, the hardware guarantees that machine instructions are always executed as if they were written in order. So when you're running on a single core machine, those instructions are always executed in order. So yeah, why can there be data races? Like, do I really need atomics and mutexes on a single core machine? Or you could change this in a bunch of variations. You could say x86, which has total store order. Do we need atomics and mutexes there? And the answer is a resounding yes, of course, because it's the compiler optimizations. And I don't know why, during my career, how many times I've needed to say this. People always think about the hardware optimizations, but we also have compiler optimizations. And just to give you an example, I have this code here. Here's some audio thread, which calls a process block. That process block is a simple gain. And it takes this gain from a parameter, which happens to be an integer, which is in %, right? But now we also have a MIDI thread that executes at the same time. That can happen on a single core machine, right? Your OS can support multiple threads on one core. And that MIDI thread might also change that gain, right? It's MIDI controllable. So if we look at the assembly that's generated by such a program, this is the assembly that would be generated, optimized assembly, if we're using std atomic. And you don't need to really understand the assembly. This is where the gain parameter is being loaded. This is where the multiply happens, and sort of this is where the loop happens. So every time you go through this loop, the gain is properly loaded. But now, if we replace this atomic with just a pure int, what will the compiler generate? It will generate this code in x86. Here we have our multiplication again. And x86 is a bit strange with FPU. There's an FPU stack, and the number it's multiplying it with is something on the FPU stack at position 1. But it's not loading anything into this position in this code, right? So it's never loading the gain in this loop here. So let's look at some more assembly. Here we see this while loop, right? And again, nowhere do we see code where it's actually loading this gain out of memory. And we need to add a bit more assembly. We need to look at the very start of this audio thread entry, and finally we see the instruction that loads the gain parameter. So the compiler optimizer, what did it do? The gain parameter, it optimized our code in such a way that the gain parameter is only being loaded at the very start of the thread, right? And so even if MIDI comes in and changes that gain parameter, your program will not see that ever. It will always stay the same. And why did that happen? Why is the optimizer allowed to do this? Well, it may assume that the gain is never accessed from another thread, because doing so would be a data race. We didn't wrap it in atomics. So the compiler can assume no other thread is changing that gain. The audio thread itself is not changing that gain, so the gain must be constant. Okay? So what this shows us, again, it's not only about the hardware. Data races can occur for two reasons: hardware optimizations and compiler optimizations. So that leads me to sin number 3, and this is something that often comes from managers, right? The managers say, we don't need extra time making this code data race free. It's always been full of data races, and it still works. So why do we need extra time trying to get rid of those data races? Let me show you an example why it might be wise to do it anyway. Same program that we just had before. And in that program, it happened to be that that read next audio buffer was in the same translation unit as audio thread entry, right? They were compiled in the same file. Now, I don't know, some point in time we change it, we move it to a different file, we put it into a different translation unit. And all of a sudden that bug that we saw before is gone. The data erase bug is fixed. Why? Well, the compiler cannot look into this read next audio buffer, right? So it doesn't know if read next audio buffer might change that gain parameter. So it needs to assume that read next audio buffer does change that gain parameter, and so it needs to reload that gain parameter every time it calls read next audio buffer. And now 10 years later, you decide to enable link time optimization, right? And the bug reappears. Why? Because during link time, now the compiler can look at all the implementations of this function. It sees that read next audio buffer doesn't change the parameter and the bug reappears. Another example, why did I make this gain be an integer for my examples? What if I change it to a float? Turns out, bug is fixed, right? Even though I didn't use atomics, it works. Why? Aliasing, right? So the compiler sees this pointer over here and doesn't know if the memory that this parameter is pointing to, if that overlaps with the parameter, with the float that is referenced by this parameter. So they could be overlapping. That means that when this code changes the memory pointed to by buffer, you might also be changing the gain parameter because they might overlap in memory. And so the compiler actually needs to reload the gain parameter for every iteration of the loop. Super expensive, right? Sample by sample, it will load that thing. So quick side note, that sounds really expensive, right? It's going to reload that thing sample by sample. What if we wanted the compiler to do that optimization? So this has nothing to do with data races or real-time safety. It's just quick side note. What if we wanted the compiler to do that optimization? What do? Well, we add a keyword called restrict. Restrict informs the compiler that it may assume that the memory pointed to by buffer doesn't overlap any of the other parameters. And I put in a side note because if I look at low-level DSP code, I never see the restrict keyword, and it's so important. Just look at your assembly, people. If you look at low-level DSP code, which deals with raw pointers, and you don't have restrict everywhere in your code, that's not good. Because if you look at the assembly, you will see many, many versions where this gain parameter will be loaded over and over and over again. And there's a fantastic talk on this by Ofek Shilon at last year's CPPCon, where he talks about other optimizations not happening where you would expect them to happen. I really, this is a really, really good talk for audio developers. I highly, highly recommend that talk. Okay, side note over. Summary, if you write data races, subtle, unrelated changes may break your code. You're changing something here, adding, link time optimizations, your code breaks. The compiler decides to do different inlining because maybe you added some stuff to your function, so it decides not to inline something else, suddenly your code breaks. Aliasing rules, you change a type, suddenly your code breaks, right? So data race bugs are really hard to track down, and I'm including this slide in this talk because I've been at multiple companies where there was a full week of all engineers hands on deck trying to fix a data race bug. Imagine how much that costs when you have 20 engineers full-time working on a single bug. That's a lot of money. And so even if everything works today, right, that's no excuse to not write your code data race free. Okay, sin number 4 is a whole group of sins which I've bunched together, which is you may never beep in real-time code, so we'll replace that beep with different things. The first thing, you may never take a lock in real-time code. So if people ask me what does real-time coding mean, and I'm short on time, then I just always say no locks, no allocations. That's sort of my short version for what real-time code means. But is that really true? And it turns out it really depends on the type of lock. So we're going to discuss 3 different types of locks: a try lock on a std mutex, a spin lock, and a regular lock on a std mutex. And bear with me, this is the longest section of the talk, but it's important. So let's look at the try-lock on a STD mutex. This is the source code of a try-lock on Linux. All the conclusions that I'm going to reach from this source code, I've been told are valid also for Mac OS. I don't know about Windows, but I'd be really surprised if the same conclusions don't hold there. So the try-lock on Linux is just a compare exchange, a single instruction. And this is obviously real-time safe, right? So are try-locks safe to use in real-time code? Probably most of you know already, right? No, it's the unlock that's not real-time safe, right? Because the unlock, if there are other threads waiting on that lock, the unlock may yield to those other threads that are waiting. So the unlock is not real-time safe. So that's the try lock. Now let's look at the spin lock. And here comes my first confession of this talk. Everywhere in that real-time 101 talk with Dave, I write the spinning just as a while and a semicolon. In all of the cast loops you see in that talk, I just write while and a semicolon. And that's a really dumb thing to do. Don't do that. You will be burning trees, right? Your CPU will go to 100% CPU usage if you do that. So never write a hot spin like this, right? There are special machine instructions just for spinning. And Timur gave a really, really good talk just on this subject, which I highly recommend as well, with different ways to back off if you're on the message thread, if you're on the real-time thread, et cetera, et cetera. This is a really, really good talk. But back to the topic at hand. Is a spin lock real-time safe? Well, if we just look at the easy parts, try lock and unlock, those are obviously real-time safe, right? Just a compare exchange and a clear. And this try lock is not wait-free. So a really good pattern that you should be using, and maybe already are, is that you use a try lock with a spin lock on a real-time thread, and you use the regular lock on a message thread, because it's okay if the message thread has to wait a bit. But here's something, a bit of a question. Does wait-free really mean it's not real-time safe? And this leads to my next confession. This is what I said in real-time 101, is that something's not wait-free, it's also not real-time safe. And I would kind of backtrack from this now, 4 years later, where I say guaranteed forward progression is more important. And let's see what I mean with this. So let's say I have 20 threads, right? And they all in a loop process some work. And when we process some work, we take a lock here right at the beginning, just a really short time. So the question is this real-time safe? And let's just consider the first thread. And by chance, the first thread can't take the lock because the second thread already grabbed it. By the time the second thread is done, the third thread grabs the lock. So the first thread still can't grab the lock. Then the fourth thread grabs the lock, the fifth, the sixth, so and so on, until the 20th thread grabs the lock, by which so much time has gone by that the second thread loops around and grabs the lock again. And so you can see this scenario where the first thread never gets the lock, right? So theoretically, although extremely unlikely, a single thread may be starved indefinitely. So this usage is not real-time safe. But let me show you slightly different code, same process work item, but now this thing scheduling the work will wait for all of these threads to finish before it starts scheduling work again, for example. Now this is okay, right? Because we have guaranteed forward progression. Let's look at that first thread again. The worst that can happen is that we have to wait n-1 critical sections to pass by, and then the first thread will definitely get some time, right? Because all other threads have finished, but this guy is waiting for all of the threads to finish, right? So I consider the above usage of this finished lock to be real-time safe. And this is a typical usage pattern, I think, in audio, right? When you need to do you have a plugin and you need to render multiple channels at the same time. You typically have this sort of pattern where you work all the channels and then you mix them at the end or for something like that. So yeah, I think spin locks can be real-time safe in certain situations. And now we come to the last one, the regular lock, right? So this is the source code for a regular lock. We're not try-locking now. And we see that there's this OS call which may block, but above this OS call, there's this compare exchange. And this compare exchange, if it succeeds, will immediately return. And what it's testing there is if the lock is already contended by some other thread, right? And this compare exchange alone is real-time safe. So what we're seeing here is that this lock is real-time safe as long as it's never contended, okay? And that may be strange, right? Like, why would I use a lock? Like, if I can only use the lock when it's not contended, why would I even ever use such a lock? And the answer is that often locks are only ever contended when the real-time guarantees no longer hold. So an example, the humble FIFO. On the left side, we have some capture audio callback. We have some audio coming in. We don't have to know the specifics here. We're checking if there's enough free space in the FIFO. We write into the FIFO, and then we update the write position. And then on here, on this side, we have some IO thread that's reading out of the FIFO, and then it's writing that to disk. So it's like a recording app or something like that. But now we need to do something with this free if we might overrun. So if there's not enough space in the FIFO, then we need to do something. And the ideal thing to do here would be to actually reset the FIFO, is to put both positions back to 0 so that we have maximum amount of room to not overrun again. That would be the right thing to do in this situation. Unfortunately, the way it's written here, it's not correct, right? Because the other thread might come in just between here. And this exact scenario was added to the Juice code 1 year ago when I was working for them. And writing this reset in a data race-free way, in a lock-free way, is super hard. It's really hard. It might sound easy. You might think double width compare and swap. All of that doesn't work, right? It's due to the symmetry. If you look at like who writes the write pause, who writes the read pause, you can sort of work out why it might be really, really hard. So I spent 1 week trying to implement it. I thought I did a good job. Then Ruben found a bunch of race conditions, and he had another week of fixing it. But if I look at the code today, I could not reason about why it works, right? It's like really, really hard. And I would recommend, if your application allows it, instead of trying to go down that path of pain, just put in a lock, even if it's not a spin lock. And why? Right? If this lock is not contended, this thing is real-time safe. But the lock is only ever contended when we have already overrun, right? So this might not be valid for every application, right? You've overrun, you're gonna get a glitch. You might get a second glitch right afterwards because this lock is contended and might swap away the operating system, might swap to another thread, a context switch to another thread, but that might be okay for your application. For some applications, it's not okay. You only want a single glitch. But I would argue for like the majority of applications, definitely consumer audio, 2 glitches in a really short amount of time, it sounds like 1 glitch. Put in a lock, save yourself the effort. Another example, here I've just put all the code you see here on this side, I've put into this push buffer into FIFO, and all the code you saw on the right-hand side, it is put into this copy from FIFO to disk. And now we want to add a feature. The user should be able to abort the recording, right? And when that happens, we want to release the resources. We delete the FIFO here. Now, of course, we can't just do that. We will be deleting the FIFO underneath, this guy's feet here. So we add a lock. And I claim that this has absolutely no downsides, right? This lock is real-time safe as long as it's not contended. It's only contended if the user has aborted the recording, right? So who cares if this thing waits really, really long? We're not gonna write this to disk anyway. This particular application has no downsides of using a regular lock. And I see people implementing this with some real-time safe code, really hard to write. Don't, just use a mutex, it's fine. And I'm going to show you a third example, which is a bit more complicated, but I think it proves the point really, really well. Here we have multiple capture devices. They all have their own threads, and they all capture this callback on their own thread, and they all have their own device ID. And for every device ID, there's some kind of mix bus structure, right? We don't really care what this does. There's some kind of mix down to stereo thing. It uses some members of this mix bus, and it pushes something into a FIFO into this mix bus. And then there's a single playback device, also in parallel can call the playback callback, and it pulls audio from all of these individual FIFOs and, I don't know, mixes them. I know this is a made up example, right? And now you've spent like a month writing this. Everything's great. Everything's real-time safe, right? This is okay to do, right? We're only reading, and we're only reading here, and when we're writing, we're using a lock-free FIFO, so everything is good. But then, of course, a month in, you need to implement the callbacks for new device added and device removed. And now things get really, really complicated. And again, writing this in a lock-free, data race-free way is super, super hard, right? Because you might be adding something to this mix buses array, right? Adding an element might reallocate it, all things might happen. So this can be really, really hard to write in a lock-free way. And in these types of cases, shared mutex is your friend. If you don't know what shared mutex is, sometimes it's called a read-write lock. Multiple threads can enter the shared lock of a shared mutex without contending each other, but only a single thread can ever enter the unique lock of a shared mutex. And this is super good if you're mixing operations which have real-time guarantees and which don't have real-time guarantees. And I think this is completely underrated in audio. I'm using a shared lock now everywhere in my code, exactly for these types of situations. And so here we have the capture and the playback callback again. We're using a shared lock because we want the simple mixing to be a real-time safe operation. So we guard those operations with a shared lock. And we know that the shared lock is real-time safe as long as you're only doing these operations. Why? Because when you're doing these operations, this lock is never contended, right? A shared lock can be entered by multiple threads. It's never contended. This code will be real-time safe as long as you're only doing mixing. Once the user adds a device, plugs in a device, or removes a device, then you take a unique lock. Yes, then this might glitch this code. But again, I think you really need to ask yourself if it's worth the effort of writing every thing real-time safe, or just to say, sure, if the user plugs out one of the device during the performance, yeah, it's gonna glitch. Like even if you wrote this real-time safe, it's definitely gonna glitch if you remove a device during a performance. And here, the way this is written, because it's only capturing, and because I'm taking a try lock, in fact, if it can't get this lock, it will just render zeros into the bus. So it won't even be, that glitch won't even be that audible in this case. So this might not be okay for your application. I'm not assuming that, right? There are applications where you are not allowed to glitch whatsoever. But I think there are many, many cases where you want to mix operations that have real-time guarantees and operations that don't have real-time guarantees. And this leads to my third confession. In the real-time 101 talk, I talk about real-time safe as this kind of binary property, right? Either your code is real-time safe or it isn't. And I say, strive to make your audio thread always be real-time safe. And I think that's wrong. I think you should rather ask yourself under which conditions you want your code to be real-time safe. And then, use locks for those operations where you say, okay, when this operation happens, I don't need to be real-time safe anymore. So this leads to the sin 4B. You may never use exceptions, and this is really quick because it's very, very similar to locks. The try-catch part of an exception is always real-time safe. It's the throwing of an exception that is not real-time safe. And again, you might ask, well, isn't this a bit useless? Like, why have a try-catch block if it can never throw an exception? Well, exactly the same thing as before. You only throw an exception when you know that the real-time guarantees no longer hold anyway. And we can, as an example, we can use the same thing. You have an I/O exception, right? If somebody unplugs a device, right? If you unplug a device, you're going to get a glitch no matter what. Your real-time guarantees no longer hold anyway, so you might as well throw in that case. And then sort of sin 4C is you may never allocate in real-time code, and closely related is, you may never use most STL containers in real-time code like string or vector or map. And it's true, right? Allocated heap memory in real-time code is definitely not safe. However, there's this trick, I'm sure many people use this trick in this room, where you sort of create a scratch allocator, you pre-allocate a bunch of memory at the start of your program on a non-real-time thread, and then this chunk of memory is used exclusively by a single thread to allocate memory. And because it's a single thread, there's no locking involved when you allocate. And you can even use this allocator with STL containers, and I'm not going to talk much more about this because Tom Maisie gave an incredible talk on exactly this subject last year at ADC, which I highly recommend. Really, really good talk. Okay, this leads me to sin number 5. So often I get potential customers asking me or telling me that their competitors' plugin, has 5% less CPU usage. And if I could take their code and make it real-time safe so that they get better performance. So let's look at a performance graph right here. This is completely made up. But this is sort of what I see in practice. On the y-axis, we have sort of the duration of some algorithm. And so that means lower is better. And then we've measured this on different machines. And we see, one algorithm performs worse and one performs better. And now, who knows what is, which of these algorithms is the lock-free version, which is the one that uses mutexes. And you might not expect what you see is that the one that uses mutexes is the faster one, right? The lock-free variant one is typically slower. And what I'm omitting here are the error bars, of course, right? So as we saw before, std mutex is just a compare and swap if it's not contended. So a std mutex is usually faster than a lock-free algorithm because the lock-free algorithm usually needs to do some kind of compare exchange loops, whatever. But the problem with std mutex is if it is contended, it takes a really long time. This y-axis is sort of logarithmic, right? These error bars are really, really high. And also, I mustn't ignore that if you have many, many threads and have lots of contention, then the lock-free variant actually also becomes faster. But I think for most code that people write in this room, audio code, that we typically write in plugins, you're typically dealing with just one thread or maybe some auxiliary render threads. You're typically dealing with 4 threads or less. So in that case, what I typically see is that the lock-free variant will be slower on average than in mutex. So don't go to lock-free code because you think it's going to be faster, right? That's wrong on average. But you still need to read lock-free code anyway, because if the mutex is contended, you might get an audio glitch. And that's especially true if you start adding hundreds of plugins to your logic project, that's when you will start hearing these glitches, because if you use std mutex instead of lock-free data structures. But this leads me to my 4th confession, and that's in the Real-Time 101 talk. We only mention the word benchmark once. And if you're not benchmarking, you're flying blind, right? I cannot emphasize this enough. You need to benchmark your code, especially if you're using log-free algorithms, because predicting the performance, even the things that I just said in the previous slides, that's mostly true, but sometimes it's the other way around, right? It's so important. If you're not benchmarking your data-free structures, then that's the first thing you really need to do. And there's another really good talk by Dave Rowland last year on how to do good benchmarks of real-time code. Highly recommend that talk. Okay, everyone's still here because now it's gonna get really complicated. If you thought it wasn't complicated enough already. So since 6 std atomic's default memory order is okay for most code. And who said this? That was me in real time. I said it exactly that way, okay? In that Real-Time 101 talk 4 years ago. And if we look at atomic instructions, we have this default memory order, which is sequentially consistent. So if you don't specify the memory order, it will always use a sequentially consistent memory order. And yeah, the confession is, over the past years, I've seen this memory order actually play an important role in performance, especially on ARM. So if you are using log-free data structures from other vendors, and you have single atomics in your code, you can ignore this part of the talk altogether, right? Single atomic load and storage somewhere, it doesn't matter if they're sequentially consistent or not. You're not gonna see your performance change. But if you're writing if you're a library developer or you're writing your own log-free data structures and they're being called on a loop or something like this, there you can definitely see significant performance improvements if you consider that memory order parameter. So I'm going to do something very, very daring. I am going to try to explain memory ordering in a really short amount of time. And I'm going to do a simplified model. And so yes, your brains will explode. I'm going to ignore the consume memory ordering because consume memory ordering is not supported by any compiler today. And the C++ there even discourages the use of this memory ordering. So the absolute ground truth for memory ordering, which also includes consume, is of course Herb Sutter's talk, Atomic Weapons 1 and 2. That's like the go-to Bible. There are many wrong talks about atomic memory ordering, even at CPPCon. This is the only one I know is fully correct. But then, and I'm going to leave this up for a while so that you can take a picture, there's a Stack Overflow answer on memory order. But it's not the accepted answer, it's not the first answer, it's like the 5th answer. But this is my go-to reference for anything memory ordering. It's really, really well written. I love that answer, so I'll just give people a moment to take a picture of that. So here comes my explanation, right? We have some kind of data structure that we want to guard, this G counter here. And we're going to guard it with a critical section. So a typical critical section here, right? We have this exchange. We set the spin lock flag to true. We do our critical thing, and then we set it to false. And then there's some other instructions which are non-critical that I put outside of this critical section because we'll be needing them. So that happens on thread 1, and then we have thread 2, and the exact same thing happens on thread 2. Now, one thing is really important to not get completely confused. Threads, so we're going to be dealing with ordering of instructions, right? Because the CPU might reorder instructions or the optimizer might reorder instructions. Thread 1's view of its own program will always be as if everything was written in order. Okay, that's a complicated sentence. But the order in which thread 1 perceives changes into memory will always be as if everything happened in order. The CPU might reorder things, but there's no way for your own thread to actually detect that. There can be no side effects of that reordering. So thread 1's operations as observed by thread 1 are always in the same order as you wrote them. But thread 1's operations as observed by thread 2 might be in the same order as you wrote them, but they might be different. Thread 2 might observe the order of thread 1's operations in a different order. Right? Particularly, it might observe some of these functions that were in the critical section being moved outside of the critical section, which would break the critical section, right? You would get a race. So that might happen in this way, but it could also happen in this way, that this instruction moves out of the critical section. What could also happen is that these non-critical instructions move into the critical section. But that's okay, right? If they move into the critical section, if your compiler thinks the code is faster by doing that, you know, having extra instructions in the critical section doesn't break any code. So to summarize, let's look at this code alone and just look at this conditional for a moment. What we don't want is instructions to be reordered to pass through this instruction upwards. What we do want is instructions to be reordered passing through this conditional downwards. So it's like a one-way street, right? It's okay if instructions pass through this condition downwards, but it's not okay if they pass upwards. And that's exactly what this acquire memory order guarantees. If you use an atomic with the acquire memory order, it guarantees that the way other threads perceive the order, it can never be that this instruction moves up, right? It can be that these instructions move down, but never up. And the inverse is true for this instruction. If we just look at this false instruction, right? We don't want instructions to move through this instruction downwards, but it's okay for instructions to move upwards. And that's the release semantics. And the release semantics can only ever be done on stores. Doing an acquire semantics on stores makes no sense. And the acquire semantics can only ever be done on loads or exchanges. And then there's another condition, is that acquire and releases always need to be paired on separate threads. and act on the same memory. If you just have an acquire operation on alone, it does nothing. If you just have a release operation on its own, it does nothing. If you have an acquire and release operation only on the same thread, it does nothing. You need to have an acquire and a release operation on separate threads, and they need to be acting on the same piece of memory, which we have here, right? We have an acquire here, we have a release here, they're acting on the same piece of memory. And this makes sense, right? When this instruction here acquires the value of the spin lock that this release wrote, the atomics will guarantee that any effects of the instructions ahead of time have actually happened before, right? So that none of these instructions pass through this store. That's what it then guarantees. Now you have to be careful about this condition that it has to be on the same memory. If I have a third thread that has exactly the same code, but it doesn't operate on the same flag, it operates on a different piece of memory, then that guarantee no longer holds. This third thread will see, again, any order of these instructions, right? Because it's not doing the acquire on the same memory. It's doing it on this myCool flag instead of the gspin flag. So, other related memory, so those are the most important memory ordering. If you understood that one, you'll understand all the other ones easily. There's also acquire and release. That's just for operations where you have like a store and a load. For example, fetch add needs to do a load and a store atomically. So it will do the acquire on the load part, and it will do the release on the store part. And then we have sequentially consistent, that's the default one. That does all the same things that we just saw with acquire and release. But in addition, this condition that they need to work on the same memory address is relaxed. If you're doing atomics with sequentially consistent memory ordering, then they can operate, then you don't need to pair them with only operations that work on the same memory location. You can pair them with operations that work on any memory location. As long as all of these operations are sequentially consistent, that myCool flag can pair with the gspin flag. Although they're working on different memory locations, on different atomics, that's okay. So that's sequentially consistent. And then we have relaxed, and this whole thing is in quotes because the whole relaxed atomics is actually undefined currently in the standard. And there's like, I think 20 papers of like what relaxed actually means. So this is sort of the quote version. Relaxed basically means the things that we expect from atomics that all the other atomics already do automatically, which is, well, they have no ordering guarantees, right? So the order in which another thread sees this doesn't matter. If you use relax, everything can be reordered. All the guarantees that things are written atomically, so no teared state, and that you ensure that there's no data races, like that the compiler cannot cache that gain parameter, right, and never ever load it again. That's all that relaxed ensures. Okay, and here as a quick exercise, we have a FIFO, a lock-free FIFO. Here we have the capture callback. We check how much is free, right? We write into the FIFO and then we store the new write pointer. And here we have the read. We check how much is available, we read it, and then we update the read pointer. So which memory order operations do we need to do for this FIFO? And the way to start is always to search for the stores, because the stores, we know, are usually release operations, right? Because an acquire operation never makes sense on a store. So we put the release operation on the store. But then we also know that a release operation always needs to be paired with an acquire operation on another thread. So we need to go to the other thread. We can't look at the same thread. We need to go to the other thread and see which one can pair with the store. And it needs to be the same atomic, so it needs to be the right pos. And so this one is a good candidate here, right? This one. So this would be the acquire. And it kind of makes sense, right? So when this thread acquires the right pos that was written by this release, we need to ensure that all of the data has been written into the FIFO so that nothing gets reordered down here. And now we can do, symmetry. This is exactly the same here. Here we have the store, we put a release here, and then we put the acquire here. It's just symmetrically exactly the opposite. And then what's left is sort of this one, these two loads. And if we look, if we observe that the write pos is only ever written by our own thread, right? No other thread writes the write pos except the FIFO writer, then we know we can use the least demanding atomic, which would be relaxed, right? In fact, if it weren't for that the store needed to be a release, then we wouldn't even need an atomic at all, because the write pause is just being used, it's just, right, this read, a data erase occurs if another thread writes to that write pause, but because we're the only thread writing to this write pause, we wouldn't even need an atomic for this instruction. But because this is an atomic variable, it is of type std atomic, we actually need to use the least stringent memory order, which is relaxed. And now we have fences. Atomic fences, what are those? So atomic fences is just a single instruction, and they just take a memory order. And if you put memory order relax into a fence, it does nothing. If you put memory order acquire, something really funny happens. Any preceding atomics instructions that you wrote, so above the fence, any atomics that have a memory order of relaxed, you can kind of think of that fence will find and replace that relaxed memory order and upgrade it to an acquire memory order. And the release does the opposite. Any following atomic instructions that had that relaxed memory order will always be upgraded to a release memory order. And we'll see an example of that later. So here we come to our last sin, and it's called std atomic everywhere, and sometimes it's also called not enough std atomic. And this is something I've struggled with over the years, and it took me really a long time to understand this part, so that's why I want to share it with you. Here we have some biquads, B0, B1, B2, and we again have a critical section to access these biquads. In one thread, one thread should be writing, one should be reading. That's a typo on these slides. Just imagine thread 2 is writing and thread 1 is reading. Now, what I often see in people's code is that they wrap these B's in atomics. All of the elements in here, they wrap in atomics, although it's already guarded by a critical section. So the question is, do we need to wrap these elements in atomics? And if you think about it, we're accessing these B's on 2 separate threads. So are we introducing a data race? So what does the standard say? The standard says a data race occurs if 2 memory operations, and now all of these need to be true, operate on the same memory, occur on separate threads, at least one of the memory operations is a store, they're not atomic operations, and they are simultaneous. So 5 things you need to check. If all of these are true, you have a data race. And you'll see what simultaneous means in just a moment. Imagine I have this code. One thread is reading, one thread is writing. There's no critical section whatsoever. Obviously, all of the conditions are true, right? One thread is writing, one thread is reading. This is not an atomic. It can happen at the same time, right? We don't know when thread 1 will be scheduled. We don't know when thread 2 will be scheduled. It can happen at the same time. We have a data race. Now let's add that spin lock flag and this critical section. But for a moment, we're not going to use atomics. Okay, so we're going to ignore reordering. We're going to ignore caches. And if we just look at the program order, there's no way that these 2 instructions can happen at the same time. If the CPU is here, then that CPU can't be there, right? So there's no data race when ignoring reordering and caches. If we don't ignore reordering and caches, right, then this thing may leak outside of the critical section, and of course we do have a data race, because now they can happen at the same time again. So if we fix this by putting an atomic here, right, last section, then the data race is gone. So we don't need to wrap these floats with atomics because we don't have a data race. So my recipe for checking if something needs to be wrapped in atomics is the following. Check for basic data race conditions, the first 4. Then assume that you don't have any cache. Assume that reordering doesn't happen, and just check if the way your program is written, if 2 memory operations can happen at the same time. And if they can't, then check with reordering, can they now happen at the same time? So these three steps. And now we're going to quickly apply this as the last slide to the lock-free FIFO again, but this lock-free FIFO now overwrites when it's full and it reads a 0 when empty. So writing a lock-free FIFO like this is the writer. Here's the write pos. We don't need the read pos because we don't check if it's full. We just wrap around if it's full. We'll just overwrite what we already wrote. Here's the read one. It just reads and replaces whatever it read with a 0. So if it underruns, it will just read zeros, right? And now the question is, do we need to wrap all of the elements of that FIFO? And this could be huge, could be megabytes. Do we need to wrap all of them in atomics? So let's do our recipe, right? Let's check these. So the first 4 conditions are obviously true. Different threads, one is a writer, one is a reader. So, but now, of course it can happen simultaneously, right? When this guy wraps around and overwrites already existing elements, this side might be reading them. So even if we're just looking at the program order and ignoring cache and ignoring instruction reordering, there's definitely a data race here. And so yes, for this FIFO, the only fix is to actually add a std atomic here. So then you would you would have to make all of these things a release memory ordering, all of these things an acquire memory ordering. That would be very expensive because the compiler would generate a memory barrier for each and every element. And this is where the fences come in, right? What we do is we replace this with relaxed, right? Which doesn't generate fences. And then we add a fence at the end. And remember, a release fence upgrades any preceding atomics with relaxed to a release. And then here we put an acquire fence, which upgrades any atomics with a relaxed afterwards will upgrade it to an acquire. So this is how we would fix that FIFO. And here's another FIFO, which I'm not going to into because I'm out of time. This is the sort of the regular FIFO that we saw before. And then here we can reason about the same thing. And we see that, our exercise before, there's no data race, even if the elements are not atomic. So for this type of FIFO, the elements don't need to be atomic. The key takeaway is, I see this quite often, is just because you're wrapping something in some kind of lock-free critical section or some FIFO doesn't mean that the elements you're accessing can be without atomics. They just, people somehow assume that doesn't need to be atomics. You actually need to very carefully check if the elements need to be atomic or not. It's not as simple as you think. Okay, so that was my talk. Conclusions, we need better tooling. It's not about lock-free or not lock-free, it's under which conditions you want your code to be lock-free. If shared lock is super, super useful, spin locks are okay in real-time code if you can prove forward progression, benchmark your code, and atomic memory order can have significant performance benefits if you use them. So, thank you.